it discharges at this lake basin. And so based on these cross sections plus some ones that I didn't show you, I was able to create three different schematic conceptual models for the region that sort of to try to explain the main modes that springs form. So the first is where groundwater intersects the surface at base level. And so in this scenario, recharge is occurring at the top of the slope here, and then perhaps preferentially travels through these tough units, where when the water intersects the surface at the base of the volcano, that's where these springs discharge. It's also possible that recharge could be occurring from losing streams that discharge into these sediments as well. And these alluvium sediments are much more permeable. So this appears to be the case for Kasima and Gaeta, Garafani, Misili, and Ngoli, which I didn't show, and Aramet. And so for the second scenario is where permeable rock intersects the surface along the slope. And so what's different at these springs is that as opposed to really being driven by this by the topography and discharging at base level, these discharge along the slope, and they're associated with this change in lithology. And so in this case, the lithology is really an important factor in spring formation, we believe. And so these are the case for the Engelin springs, Engelin, Angina, and Tane. And then the third scenario is just this unique case, Isiri, where because of all the fractures seen at the surface in the tufa mounds, and the warm water temperatures and high ion conditions, we believe the water here is traveling deeply until it reaches these fractures where it's under pressure moves to the surface. So I just want to say before I get to the conclusions for this chapter, that I think that these conceptual models are really important to start understanding how these springs are forming. And they also can be used to compare to springs in other areas, other rift valleys. For example, at the Dead Sea, there are a lot of springs that persist also at the base where in this rift zone, so where these extensional processes are going on. So to conclude, here's what I contributed to these physical framework and hydrological inputs. So we created 3 schematic conceptual models, one where groundwater intersects the surface at base level, the other where the permeable rock intersects the surface along the slope, and the last where artesian flow at fractures under hydraulic head. And then in terms of the water quality, it's all very acceptable for drinking based on the EPA standards, except for fluoride, which is known to be pretty high in the rift region. And then the stable isotopes gave us information to understand that the local atmosphere is sourced both from the Indian Ocean and perhaps recycling also from the rift lakes. In terms of the hydrological inputs, it was to better understand the temporal and spatial rainfall patterns across the study region. We're able to see, based on the rainfall data, see this orographic effect where the highlands receive more rainfall than the lowlands. We're able to see that there are these 2 clear wet seasons, the March through May and October to November. And then also the El Nino Southern Oscillation and Indian Ocean Dipole don't appear to be the best predictors of rainfall cyclicity on these interannual scales. Okay, so that concludes chapter 1, and now I'll move on to chapter 2 in lightning style. Okay, so what are wetlands? So wetlands are land areas that are saturated with water for at least part of the year, and they exist in a space that's in between terrestrial ecosystems and aquatic ecosystems. And so they provide numerous benefits to society. They can attenuate floods, they can improve water quality, they provide refugia for biodiversity, and they can capture carbon, so many benefits. And you can see that they exist based on this image here. They're distributed all over the world. You can find them in every continent except Antarctica, and in every climate from the tropics to the Arctic. And so while their values are really recognized today, wetlands are a relatively new field of study, and especially among geologists. In fact, classic facies models textbooks have yet to really include wetlands as a depositional environment. So that's sort of my motivation for today, is to better understand wetlands in a geologic context. So as I mentioned, my objective is to try and characterize wetland deposits in a lithologic record, determine if a facies model could be created for wetlands, and then try try to do a little bit more, which is to see if a facies model for wetlands in each biome could be created. So based on the averages precipitation and temperature, whether this would impact the deposits to give them distinct features in each biome. So first of all, what is a facies? It's not multiple facies, which you might be thinking. So a facies model is a general summary of the physical, chemical, biological features that exist in a sedimentary succession that indicate that these deposits come from a specific environment. And so you can't just look at one outcrop and say, okay, that is indicative of this environment if you want to make a facies model. What you need to do is you need to kind of do a literature search. You need to look at many different local examples. And so Walker's the one who first talked about facies models, and he calls it a distillation process, because what you do is you want to look at many different case examples, and you want to sort of distill what you think aren't just the noise, the local effects, and just get the specific things that exist for that unique environment. And so facies models can be used for many different purposes, and so that is what I'm trying to do today. And so the ways that I'm doing it is, I looked at modern and ancient deposits identified in published documents. I chose study sites from each biome of the world, so some from tundra, temperate forest, rainforest, desert, savanna, grassland, and taiga. And then I compiled information for each site, including wetland type, formation, local climatic setting, lithology, biology, geochemistry, wetland age, into these really boring